Welcome to this video on more about changes in magnetic flux. In this video, I'm going to take just a minute to explain to you some other variations in how you can manipulate flux in terms of the angle between the magnetic field and the area vector, because I think that's sometimes confusing, and in the last video we covered some of the basics of that, but I think we can benefit from a little bit more different perspectives on changing flux. So if we remember magnetic flux, which we symbolize with the Greek letter phi, I'm going to change the M now to a B. That's oftentimes standard as well, and I just want to make sure everybody knows that that can switch between a B and an M. So the magnetic flux here, remember, is the amount of magnetic field times the area that the magnetic field is passing through, and that's a dot product. And so another way to write that exact same statement was BA cosine theta, and that's what we showed in the last video. We've also established this idea that you can establish a potential difference, or you can establish a voltage if you change the magnetic flux over some amount of time. So the quicker you change it, the more voltage is generated, and vice versa. So what we want to look at here is, how does this angle, how is it possible that this angle changes, and just again, what is that angle in particular? So over here I have three different situations set up below, and what we're looking at is just a segment of a magnetic field. So this would be the North Pole, and you can imagine like this magnet kind of is a horseshoe magnet, so it connects to this other part, which is the South Pole. And so we're just looking at a very small portion of the magnetic field. Now keep in mind, you don't get, so far as we know, individual monopoles. So you can't just have a North Pole magnet or just a South Pole magnet. This would actually be connected. I'm just not showing it in these pictures. So in all of these variations here, we see that the magnetic field B are the blue lines. So I'll go ahead and write that in here so we can see that. Now, we have a loop. You can think of it as a hula hoop, and you can think of the blue lines as rain. And right now what I'm going to say is the hula hoop's facing upwards. So I'm going to draw an arrow here, and I'll try to draw that as a straight line. We're going to draw this arrow here as representing the direction of the area. So that the area is facing up like this. Now what I want to do is I'm going to turn this hula hoop about 45 degrees clockwise. So kind of turn it in that direction, okay? So now I see that the area is pointing in that direction, all right? And then I'm going to keep turning it another 45 degrees so it comes down to this side. So now the area is pointing over here to the right. So we have three different segments of the same kind of motion. Now, if we think about what magnetic flux actually is, magnetic flux is the amount of field passing through the surface. So if you look here and you think of this as rain, you can see that all of the rain here, 1, 2, 3, 4, 5, 6, 7, 8 lines of rain are passing through this surface. And if you think about the angle between this vector A and the B vector here, okay, you see that there's 180 degrees here as I've drawn it, and if you flipped it all the way around, you'd have 0 degrees. So we would say that there's 0 angle here between the two. Now a lot of students will think, well, I see that as 90 degrees because I see this flat face here and it's perpendicular to the field lines. But remember, we're measuring it from this angle, not from, or from this line, the area line, not from the face of the hula hoop. Okay, in this case over here, we see that there's going to be an angle between the field over here and the area. So now not all 8 lines are going through. 2 of them are not anymore because of the orientation. So here all the rain went through. Here we're missing 2 lines of rain going through, if you will. So there's a 45-degree angle between the two. Okay, and if you think about it, the cosine of this angle, 0 degrees, is going to give me a value of 1. The cosine of 45 will be less than 1, right? So if I put here the cosine of 45 degrees, that's going to be a value that is less than 1. So we can see here that the amount of magnetic field passing through the loop, or the flux is decreasing as we work our way across. Here we see a 90-degree angle between the field and the area vector. So at this point where we have 90 degrees, we know that the cosine of 90 degrees is equal to 0. So what's happening here is the coil is spinning this time, rather than in the example in the last video where the magnet was turning relative to the coil. And we see here that as this coil spins, the flux decreases. And now if I keep turning it, right, we'd see the flux start to increase back again, and then decrease and increase. And you can think of this as spinning around in this magnetic field. So the key is that the flux is changing, and then how quickly that happens will determine how much potential difference is formed in this loop, which is really interesting. So in essence, by spinning this piece of wire, this loop, this hula hoop of wire in this magnetic field, I generate electricity in this little loop. So there's no power supply. It's this relative motion, this change in the flux over time, that's causing the potential difference, or the electricity. Now, what we see happen here is that as it turns towards this position, the direction of the magnetic field, the direction of the current in the loop is going to flip when it starts to go back up again into the other orientation. So this is what we're going to start to see now, is that the current in the loop changes direction as the loop rotates. And that's a really important idea, and that's what we're going to take a look at in the next video, and that is known as Lenz's law. And it's a very important law in electromagnetism. So we'll check that out in the next video.